Hello everyone, my name is Jo, and it is my honor to present at the 21st Kwix program. In the research group of Professor Seung Go from the Department of Electronic Materials Engineering, we have developed a strain gauge sensor with our circuit based on closed-loop calibration, aiming to enhance accuracy and reliability in measurement systems. We'll begin by introducing the background and motivation of this work, then move on to the circuit design, followed by experimental research, and finally conclude with a summary. The smartphone market is continuously expanding, but its user interface is still mostly limited to physical button presses and simple touch inputs. This makes it difficult to expand functions beyond the basics. To overcome this limitation, we came up with a new idea for an integrated module. Instead of pressing buttons, our system takes input through the pressure of a finger, providing a more intuitive and interactive experience. So let me walk you through the overview of our system. As you can see here, this module uses a button structure based on a strain gauge. Basically, when a finger presses the button on the side, the resistance inside the SoC changes. And because of that, the current also changes. Now, inside the chip, this current is converted into a voltage signal, and with this voltage, the chip can decide and perform the proper operation. Now, let me show you the overall block diagram of the circuit. The key components include the regulated cascade structure, a calibration loop, a CC2, a Q2V converter, and a DAC. So let me briefly explain how the circuit operates. First, when the burn resistance Rs changes due to environmental factors, a mismatch occurs between the current of the NMOS and PMOS devices. This mismatch creates an offset current, and in the closed loop, this offset current is processed through an I2V converter and an integrator, which generate a voltage. This voltage is then stored in the ADC, passed through the LUT, and finally updated to the DAC. The DAC applies the corrected voltage to the PMOS in the regulated cascade. As a result, the current flowing through the PMOS and NMOS is balanced, and the offset current is significantly reduced. Then, when finger pressure changes Rs again, the balanced PMOS current and the newly changed NMOS current create a small difference. This difference flows to the readout path, goes through the Q2V converter, and recognized at the output as a voltage input. Next, let me explain the role of the regulated cascade in our circuit. It is mainly used to sense the current flowing through the resistor in a stable manner. If we only use an NMOS device by itself, sensing the current directly causes an offset, which makes the circuit operation unstable. To solve this offset problem, we designed the circuit in a regulated cascade configuration, pairing the NMOS with a PMOS device. This pairing helps maintain stability while accurately sensing the current. Now let me talk about the calibration loop. The purpose of this loop is to compensate for the initial offset of the burden resistance, which can be caused by external factors such as temperature variations. When a current mismatch occurs, the op-amp together with the integrator detects this difference. Then, through a DAC update, the loop adjusts the bias so that the currents flowing through the PMOS and NMOS are balanced again. As a result, when the calibration loop is operating, the current flowing into the readout path gradually converges to zero, ensuring stable operation of the system. Next, let me explain the 9-bit double R DAC circuit. This DAC operates with a 9-bit input signal. In the first stage, the front 6 bits cover the full voltage range. Then in the second stage, the remaining 3 bits further subdivide the range based on the VH and VL generated by the first stage. In this way, the circuit is able to produce a more precise output voltage while still maintaining a wide overall range. Now let me introduce the structure of the CC2 used in our circuit. In this design, the CC2 is used to convert the voltage variation caused by the resistor change into current. The main purpose here is to prevent saturation of the transfer current, and in other words, the CC2 helps reduce the magnitude of the output current, keeping the operation stable. In our simulation, we applied an HL100 bit input signal, and as a result, the output current of the circuit was set to about 5 of original current level. Now, let me explain the simulation environment along with the control signal sequence. So, to represent the user input, we set the resistance to change over time, from 10 kilo ohms down to 9 kilo ohms and then up to 11 kilo ohms. And if you look at the right side of the slide, you can see the sequence of the control signal plotted over time, showing how they are applied during the simulation. Next, let me show you the DAC output waveform. First, in the 6-bit DAC, the voltage range is set across the full range of 0 to 3 volts. Then in the 3-bit DAC, the voltage is adjusted more precisely, moving closer to 1 volt. And after that, by applying the HHLL signal to the embedded DAC, the final DAC output is confirmed to be approximately 0.9999 volts. When the calibration signal is applied, the circuit matches the current of the MOS and PMOS within about 6 microseconds. And at that point, the voltage generated in the loop is stored through the ADC and then updated to the DAC. After the calibration signal is applied, the current difference between the PMOS and NMOS is in the regulated cascade becomes approximately 2 nanoamps, which is almost zero. Because of the signal stored in the DAC, a fixed current flows through the PMOS. Meanwhile, any current variation caused by the change in the R button connected to the NMOS flows out to the readout path. After that, the current difference caused by the initial change in the resistance is converted into an output voltage once the readout enable signal is applied. As a result, the output shows a sawtooth waveform, as you can see in the figure. Finally, to summarize our work on the strain gauge-based readout circuit. The circuit demonstrates a great and stable sensing performance. In addition, it operates reliably even under environmental variations, eliminating signal distortion and reducing the risk of malfunction. Overall, this design shows the potential to replace conventional mechanical buttons and provide users with a more convenient and innovative interface experience. This concludes my presentation. Thank you for your attention.